Okay, here we go. We've introduced the idea of properties of a system, and we said that we have extensive and intensive properties. Now, there are multiple properties that we're going to talk about throughout the semester. There are three properties that it would make sense to measure, and that would be, which we mentioned on the previous slide, temperature, represented by capital T in our text. Some texts will use the Greek letter capital theta to represent temperature. Your text does not. Your text uses capital T for temperature, lowercase t for time. Pressure in this text, we typically use a capital P to refer to pressure. You'll want some way to have an idea what a capital P versus lowercase p looks like for you. Mine are not terribly indistinguishable, but anyway. Volume. I cross my capital V when I'm referring to volume. We'll see why in just a little bit. If I'm referring to other quantities, I don't cross the V. If I cross the V, it's referring to volume. Again, we'll talk about why probably by the end of this video. Three properties we could feasibly measure. Properties I could not feasibly measure. In the previous videos, we talked about the first law of thermodynamics, conservation of energy principles. Right? So there are different types of energy, for example, like the internal energy of a system. That's something that is not feasible to measure. It's not easy to measure directly. The entropy of a system, the chaos, how unpredictable are the particles? Not easily measured. These are three properties, but those are two properties I'm going to need to know to satisfy or to solve the first and second laws, but I can't find those directly, or at least not easily, if at all. But these are properties that I can directly measure. So these are properties that we're going to focus on initially. So if we go through and break down these properties a little bit, let's talk about temperature, volume, and pressure. Now, I'm going to do this on the document camera. So I'm going to stop share, and I'm going to change video feed here. We're going to go to the document camera. Like I said, I got a different document camera. Used this last summer to record some videos for statics class. I think it works better than my GoPro. Hang on. I'm going to pause here. I apologize. It was set on rapid autofocus, and I didn't like that. I wanted to stay focused because this isn't moving around a bunch. So anyway, I think we're good now. This is lecture one. This is going to be paper two of something, so I'm a little more organized. By the way, if you're using engineering paper, these are good for putting things like name and homework number one, and maybe additional information, date, something like that. Put your page numbers up here. Put a staple right here once you get all your sheets together if you were turning them in. But since you guys, for me in my class, you're scanning these as PDF, you wouldn't have to staple them. Anyway, have questions about using engineering paper, please let me know. Don't write on the backs of your engineering paper. That should be criminal. But at any rate, let's continue. What were we talking about? We're talking about volume and friends. Volume and friends. Okay. Capital V with a cross through it. This is total volume. It's total volume. This is how I will draw this is how I'll draw V when I'm referring to volume. If you see this symbol, looks like kind of a lowercase p, and I tend to draw a little backwards tail on it. This is how I will draw a rho. This is density. This is density. If you remember from chemistry, density is mass per unit volume. Now, something you may not be familiar with is specific volume. That is lowercase v. This is specific volume. Right, so this is how I draw a lowercase v, where I'll put a sharp corner in the bottom of a capital V. I don't put that sharp corner in the lowercase v. I will try to draw it smaller. You see, I'm taking up like 3 or 4 lines for a capital letter and only a couple lines here for the lowercase letter. This is specific volume. Specific volume is volume specific to mass or volume per unit mass. It is the reciprocal of density. By the way, notice as I said, I put a backwards tail on my lowercase rho because if I don't, it looks an awful lot like my P. I don't have a good way of differentiating between a rho and a P, so that's what I do, is I'll put a backwards facing tail on that. Okay. There is also, you'll encounter sometimes specific gravity. Specific gravity of a substance would be the density of your substance divided by the density of liquid water. Right? And so for our purposes, uh, for liquid water, the density of liquid water is about 1,000 kilograms per meters cubed. Oh, sorry, you can't see that. I cannot stress this is for liquid water. I cannot stress that enough. It's for liquid water. About 1,000 kilograms per meters cubed is always fine. It's like 999.7 or something like that. It's also about 62.4 in the English units. That is pound mass per cubic foot. So if it's liquid water, either of those are okay. Once you get past chapter 3, you're not going to be able to assume liquid water anytime you see water because we're going to learn how you can tell what phase that water's in. But for the most part, in chapter 2, if you've got water, it's probably in liquid phase. These are the densities. And again, that's important because sometimes the problem will give you the specific volume or specific gravity, sorry, the specific gravity. Specific gravity of your substance is the density of your substance divided by the density of water. So something with a specific gravity of greater than 1 means it's more dense than water, means it's going to sink. For example, mercury. Mercury is like a 13.5 is its specific gravity, or somewhere in that range, between 13 and 14 times the density of water. This is a very, very dense substance. Okay, that would be specific volume and friends. Mhm. Okay. Or volume and friends, I should say. Now, if we talk about other properties here, other properties, again, pressure, temperature, and volume are the three properties that we can feasibly measure. So if we talk about temperature, what does temperature mean? What does it mean for us to be hot or cold? But if I say, well, it's cold in my classroom because it's summertime and our air conditioner is full blast and we seem to get the coldest air first and other buildings get kind of warmer air. What does it mean when we're cold? Well, it means that it tells us about how our body is perceiving heat transfer, the direction heat is moving out of our body. So if we feel cold, most likely that means we're in an environment that is cooler than our body and our body is losing heat to that environment. If I feel hot, that could be I'm in an environment where the outside is hotter than my body. And so I'm feeling heat coming in. It could also mean that I've just like worked out or exercised and my body is hotter or higher temperature than it's used to feeling. And so my skin cells are feeling heat moving through them, either from the core or from the outside, but I'm feeling hot. So it's kind of when you feel hot or cold, it's you have to think about and understand what are your nerves in your body telling your brain. And we have to try to figure out what that how that means and how that affects us. But if I say, hey, it's 1 degree Fahrenheit warmer or cooler, can you actually like tell that? Can you feel that? Do you know what 1 degree Fahrenheit or 1 degree Celsius is? that's a little more of a challenge, right? It's kind of hard to perceive. It's not like I can just put a kilogram in your hand and you can feel that kilogram. Um, it's really just kind of more of a feeling to us, but it is a quantity that we can measure. And what it does is it allows us to measure the direction that heat will flow if allowed to flow spontaneously. And actually, heat will always flow from a higher temperature body to a lower temperature body. So how do we measure temperature? Well, we could use like this glass thermometer you see here, where I put inside of a vacuum tube, I'll put some sort of a substance like alcohol or mercury, and we apply a temperature down here on the bulb, and that causes expansion. And that's a predictable expansion that expands against some scale here. And as that liquid expands along that scale, we basically can measure its change in length, and that tells us a change in temperature. We can also use, you kind of see these ray gun looking things that you point at an object and pull a trigger, and it basically measures kind of the black body radiation. It measures kind of the infrared emissions. It's literally kind of measuring other properties to determine the temperature. We can also use voltage change between two metals. Metals will kind of when I put two metals together, they'll emit a voltage, and that voltage changes sometimes depending on how the temperature is. So there's all different kinds of ways that we can measure something that tells us the temperature. So it's a little more difficult to quantify, but what we do know is that if I have something at a higher temperature, that tells us the direction heat's going to flow. Heat is going to flow spontaneously from the higher temperature to the lower temperature until it reaches equilibrium. So a piece of ice, you put it in a normal room, unless the room's really cold, that ice is going to melt because the ice is going to absorb heat from the higher temperature room. Right? And it'll do so until both the room and the object reach basically the surroundings and your system until they reach an equilibrium. They will continue to exchange heat. The higher temperature body will emit heat to the lower temperature body, right? So, and by the way, when you see kind of this gray shaded area around something here, right? Um, Let me pull my pen out here. Oh, I don't have my stylus up. That's why, right? So when you kind of see this gray shaded area around something, they're saying that that is insulation. And if I'm drawing insulation, I'll probably do something kind of like what I'm doing right here, kind of this squiggly line around something. That tells us we've insulated that. So if I put a hot chunk of metal next to a cooler chunk of metal and I insulate them, I basically try to prevent that system or those objects from interacting with the surroundings through heat transfer. That means all the heat is now trapped between those two, or all the energy is trapped between the two, and they're just going to exchange energy until they reach an equilibrium. Now, we've mentioned the first and the second laws of thermodynamics. There's actually three laws of thermodynamics we're going to talk about in this course. We won't talk much about the zero or the third. We'll just mention them, and they're basically these statements that we can't prove them mathematically with the other laws of thermodynamics or other laws of physics. They're their own statements. So they stand alone as their own laws. So this is the zero law of thermodynamics, and that says that if any two bodies are in thermal equilibrium with a third body, that means that they are in equilibrium with each other. So I've got a mouse sitting in front of me, a computer mouse, and I've got my cup of water in it. So if both of them are in equilibrium with the room around them, that means they must be in equilibrium with each other. And you can probably pick out objects on your desk or wherever your couch or wherever you're sitting, that you could say the same thing about those. Okay. How do we measure temperature? Well, in the SI system, if you've grown up outside the United States, there's a very good chance you think in units of Celsius, in degrees Celsius, right? It's a perfectly valid way of measuring temperature. For the rest of the world, water boils at 100 degrees C and it freezes at 0 degrees C. For those of us that have grown up in the United States or spent a lot of time in the United States, we tend to think in Fahrenheit. So for us, 0 degrees Celsius is like 32 degrees Fahrenheit. And water boils then, where it's 100 degrees Celsius, that for us is 212 Fahrenheit. So it's always it's funny when I'm playing an online game or something like that, and I'm talking to people in other parts of the world, and they say, "Man, it is 85 degrees, it's like 90 degrees outside. It's kind of warm today. And they're like, oh my gosh, are you dead? Because to them, 90 degrees that's people die at those temperatures. Where for us in the Fahrenheit scale, no, 90 degrees is just really, really warm, but it's not like unbearable. So those all are at one atmosphere pressure. We're going to talk in chapter 3 about how pressure affects where these points occur. But at the standard atmosphere, where basically if we're standing at sea level, we're going to talk about pressure here very soon. If we're standing at sea level, one atmosphere is basically the pressure of all of the air above us, and before you get to space, pushing down on us. All right, that's a good place to stop and pick up the next video. I'm a little over 15 minutes. That's what we're going to do here.